All right, so today we're going to talk about like heat pumps and air conditioners. So a heat pump, basically, it kind of works exactly like a heat engine, but kind of in reverse. And refrigerators, they all work. It's very similar to this drawing here. So this we're referring to heat pumps and refrigerators. Well, what they do is they remove heat from the system, right? And there's a process. So then, if you look at the pressure versus the volume, essentially, a cooler heat goes into the system mainly because you're withdrawing the heat, you're extracting the heat out of the system. And generally, you're going to have to put some work into the system to facilitate that process. So, in general, we have the high heat is equal to the cool heat plus the work that goes into the system. Now remember, when we enter into the system, so let me write that down too, because I think that's what we were talking about that earlier. In is positive. We're adding it into the system. Out is negative. Okay, and when I say system, what I'm talking about is this right here, whatever that system is. Okay, could be your bedroom or living room at your house and you have air conditioning, but I think the important thing to look at when we look at these PV diagrams is if you start at A, it's just notice that the direction of the arrows are opposite. So as you draw, and think of it in terms of this, as you pump the heat out, that's why they're called heat pumps, what happens? Well, the pressure sort of increases, but the volume decreases, right? Or, however you want to look at it. And then as that heat continues to leave, the colder temperature can come in. And so then the pressure lessens a little bit, but the volume also lessens too. And in the adiabatic compression, what happens is that at some point the pressure increases and then the volume decreases, and then from here to here. So it's kind of a different type of model. So it's basically like a heat engine, but backwards. So heat pumps and air conditioners and refrigerators are heat engines. They operate backwards. Yeah, I mean, that's basically it. So this principle of the high heat is equal to the cold heat plus the work going into the system is how you make all the calculations. Can I move on to the next slide? You guys have that drawn? All right. So then the next thing is, let me see if I can get this copied over. There we go. So this image here is basically how a air conditioner works, or a simple heat pump. It has four basic components. The first component is the condenser. That's this right here. The second part is the expansive valve. That's this part here. And the third part is the evaporator, because when you cool off air, the moisture that's trapped in between the air molecules, the water molecules trapped, the air can absorb more water when it's hotter. But when you cool it off, that water falls out of the air. And then lastly, you have 4, which is the compressor. So in heating mode, the heat transfer QC occurs to a fluid in the evaporator. And from a colder outdoor air, turning it into a gas. The electricity or electrically driven compressor increases the temperature and pressure of the gases and forces it into the condenser coils, okay, inside the heated space. Because the temperature of the gas is higher than the temperature in the room, the heat transfer from the gas to the room occurs when the gas condenses to a liquid. Working fluid then is cooled back through its expansive valve and the outdoor evaporators. So they're using a coolant, which is a liquid at a certain temperature, and they go through this process. It starts at the condenser and works its way around here, and just keeps repeating, and really what it's doing is it's extracting heat out of, right? So outside, if it's outside, normally that is going to be a little bit cooler than the inside of the house. Okay, why? Because the evaporator is blowing air, right? The compressor will change the pressure. The condenser does its part, but it also extracts the heat out. That heat gets absorbed by the fluid, and then the fluid transfers it to an expansion valve, and then the process repeats, okay? And so what's really going on is the electrically driven compressor, this compressor does work into the system. All right? So again, I'll write this formula down again so you know that the high heat is equal to the cool heat plus the work. Okay? So because the temperature of the gas is higher than the temperature inside the room, so why is it higher? Well, because we did some work to it, right? By increasing the pressure, we increase the temperature. Does that make sense? Okay. So because we did some work to it, we're able to increase the temperature. Then the heat transfer to the room occurs, and the gas condenses to a liquid. Okay. So these coolants can be gases. In fact, it's funny when you put coolant into it, and like especially if you do it with a car, it's like a gas. But then when it goes through the condenser, it eventually turns into a liquid. And so then the quality of the heat pump is judged on how much heat transfer QH occurs into the warm space compared to how much work input is required. And so if we want to talk about a heat pump's coefficient of performance, you just take the ratio of the high heat over the work that goes into it, okay? And we should also remember that the efficiency of a heat engine, so this is a heat engine, is equal to the work over the high heat. So what does that tell you? They're reciprocals of one another. So the efficiency of a heat pump, and it's basically just because we're doing the work backwards, okay? So what that means is there's a mathematical relationship between, this could be written as this, 1 over the efficiency of the heat engine. And we'll do lowercase h, e, heat engine. And since the efficiency of any heat engine is less than 1, that means that the coefficient of performance of a heat pump is always greater than 1. So how do I want to write that? So this is always greater than 1. This is always less than 1, right? Does that make sense? Okay, because we're reciprocating that. So then the other thing that we should probably talk about, our Carnot engine. So Carnot. Remember, Carnot came up with this brilliant discovery that the efficiency is 1 minus Tc over Th, right? The temperature of crap, I can't think of the word. Where it's the temperature. I can't think of the word. But anyways, it's the room temperature or the temperature difference of these two spaces, right? So so then if we study that and we rewrite it in terms of the coefficient of performance of a heat pump, because this is 1 over that, that could be written as 1 over 1 minus Tc over Th. And you could do some math here if you wanted to, which would be kind of problematic, but you could do some things to kind of toss the Tc and Th to the top if you want to, or you could just leave it like that. So heat pumps do not work as well in cold climates as they do not have more moderate climates. So basically, the smaller the temperature difference, the smaller the efficiency, and the greater let me think of a way to. So, remember this, if this has a very small temperature difference, right? If this approaches 0, you have a very high efficiency, right? If there is a very small difference, then this, so this is, this would approach 1, the number 1, right? And 1 minus 1 is 0, so you would have a low efficiency. Okay. So how does that have an impact on the coefficient of performance? So if there's a high difference between Tc, Th, and it approaches 0, in other words, that ratio approaches 0, you're going to have a very low COP, right? Because if this approaches 0, you have 1 minus 0, so it's going to be 1 over 1, right? But if you have a huge difference, if no, this is a huge difference. If you have Th and this approaches 1, then you would have like undefined, right? So as this approaches 1, you're going to have this decimal on the bottom, but you reciprocate it, so then you'll have a very high coefficient of performance for the heat pump. And so when I say lower, this what really happens is that in this scenario, COP approaches the value of 1, because it's almost like 1 divided by 1. Okay. Now, there, like anything else, right? Friction and other irreversible processes reduce the efficiency. These compressors have moving parts and stuff like that. Molecules are bumping into each other, air molecules or the gas molecules of the coolant, stuff like that. And so in reality, does everybody have this written down? So in reality, what you're dealing with is something similar to this. Okay? So you've got work coming into the system, right? Remember that, oh shoot. And I'll keep writing this down because it's important. QH is equal to QC plus the work. So in general, you have work going in. But now that work, some of that work overcomes friction. And that friction releases, whenever you have friction, you have heat. And it could be anything. It could be the moving parts, right? There's a fan that's blowing, like it could be that. It could be the molecules and the gases. Then when they become a liquid, it could be that. That all has to be released. But eventually, once the part that's used up for friction is kind of gone. It goes back to the outside, right? Remember in this model, this is kind of, well, we'd have to go back. Let me just go back and remind you guys of how that works. We have outside and we have inside, all right? And so that's what we're trying to figure out is what is outside, what is inside. Well, outside for the most part is over here. Okay. But in reality, the system is the room on the inside. But there's also this loop where we take the heat and we do all that stuff. So it looks more like this. So all this stuff happens inside, and then the outside's the cooler part. And the system could be the air conditioner. So anyways, back to before I get sidetracked. So we lose a little bit, so it's not efficient. And I can't go backwards. In other words, once this heat from friction is gone, it's gone. It's not going to go back this way. It can't. Okay? Once I do work with the mechanical stuff, it's gone. It's not going to come back. Okay? So the work goes into the heat transfer before it even gets into the heat engine, thereby reducing its coefficient of performance. Where work prime, right, this right here, is the portion of the work that actually goes into the heat pump. So you have your work. Well, what is the work? Well, it's going to be the work prime plus the heat due to friction, right? So it's getting divided up. And mathematically, the plus or minus depends on the system. Like some of it goes in, some of it stays out. So we'll circle back to this on the sign, right? Plus is going into the system while minus is coming out of the system, right? And when I say system, I mean this circle right here. And you see how they have it drawn? They have it like kind of, some of it's in the system, some of it's out of the system. Okay? All right. Let's do an example problem. And we'll see if that makes this a little easier or whatever to understand. I like doing the example problems. They can help. All right, does everybody have this written down? Okay. So ideally, because of this information, we want to make, there's a big, huge search for efficiency, right? And heat pumps are really nice because you're basically pumping heat out of the room, okay? So a heat pump is used to warm a house You can warm the house, like you could pump heat into the house, or you could pump heat out of the house. And it's just a reversal of the process. So a heat pump is used to warm a room, must employ a cycle that produces a working fluid at temperatures greater than the typical indoor temperature, so that the heat transfer to the inside can take place. Similarly, it must produce working fluid at temperatures that are colder than the outdoor temperature, so that the heat transfer occurs outside. It's hot and cold reservoir. Reservoir was the word that was escaping me earlier, right? The temperature reservoirs, the high heat and the low heat, the high temperature, the cold temperature reservoirs. Therefore, it cannot be too close, placing a limit on that coefficient of performance. What is the best coefficient of performance possible for such a heat pump? If it has a hot reservoir of 45 degrees Celsius and 15 degrees Celsius. Okay, so we start off with the efficiency. So the efficiency of a Carnot engine, right? We're assuming this is ideal, right? That was Carnot's big thing. And then we'll plug this in, right? So where I'm going with this is we know that this is that COP is equal to 1 over efficiency. So I'm just going to calculate this because I have the numbers. So I have 1 minus, and you gotta, here's the funny thing, you gotta convert this to Kelvin. So TC, if you add 273 to that, it becomes 258 degrees. And then if you add 273 to 45, you get 318. You guys know what I'm talking about, right? Okay. So then the efficiency of this is about 0.1887. And this is Kelvin. This is Kelvin. Okay. So then my coefficient of performance for my heat pump is just going to be 1 over the efficiency, or 1 divided by 0.1887, or 5.3. Now, we also said, this is an interesting thing. I don't know if you remember this, but at the very beginning of our notes, we said that our coefficient of performance is the same as the high heat divided by the work. And we happen to know that that's 5.3, right? So then what we do with this is why it's called the coefficient of performance. If I multiply both sides, I end up with my high heat is going to equal 5.30 times the work that I put into the system. And that's why we call it the coefficient of performance for a heat pump. So what does this mean? Well, it means that the heat transfer by a heat pump is 5.3 times as much as the work you put into it. So if you want more heat, put more work. Does that make sense? Okay. Any questions on that? So let's put I'm going to put an image up here. So you can kind of get an idea of what we're talking about. So this is a wall, this is outside the house, this is inside the house. You have colder, negative 15 degrees Celsius is cold. 0 is freezing, so this is really, really cold outside. 45 degrees on the inside is really kind of hot because room temperature is 20 degrees Celsius. Well, why is this so hot? Well, it needs to be in order for everything to work. So this is a heat pump, and what we're doing is we're taking and we're pumping heat into the house through this process, okay? And so the outside temperature of the air is -5. The inside the house, we want it to be 20 degrees Celsius. And then the actual heat pump works this way. They have a difference between the two temperature reservoirs of about 30 degrees Kelvin. Oh, no, wait, it's greater than that, from -15 to 45, whatever that math is. 60, right? 60 degrees difference. All right, so, I mean, that's basically it. Notice that the cold temperature produced by the heat pump is lower than the outside temperature, so that the heat transfers into the working fluid. In other words, this will absorb heat because this temperature, right, is higher than this one, right? Remember, heat always flows from the highest temperature to the lowest temperature. So this heat pump actually makes sure that it is colder, right? Do you understand what I'm saying? This is colder than this. So the heat from the outside air, even though it's really cold, is actually going to transfer in. We have some work done here because we plugged in our heat pump. When we do the work, we have a high heat here. So we have cold, still heat though, coming in plus the work. And when you add those together, that'll give you more heat. I don't know if that helps. So real heat pumps do not perform as high as 5.3. Generally, their COPs are anywhere from 2 to 4. Okay. All right, we'll talk about air conditioners a little bit. You guys done writing all this down? So an air conditioner is a heat pump, but we just do the same thing but backwards. And I'm trying to make that smaller. It won't let me make it smaller. There it goes. So that was a heat pump, how you take, even though the air outside is cold, you create a cold reservoir that's colder than the air outside. The heat from the outside transfers into the colder reservoir. That heat gets transferred in with some work, and the work plus the heat heats the inside of the house. Okay? Now for our air conditioner, the coefficient of performance for a refrigerator or air conditioner or some sort of refrigerator is actually QC over the work. Okay? Which makes it the complement of a heat pump. So the coefficient of performance of a refrigerator is actually equal to the coefficient of a heat pump minus 1. And I don't want to bore you guys with like the references, but if I take this and minus 1, I'm going to get, remember that it's the reciprocal of the efficiency and all that stuff. So it works out. It's a derivation. Okay? So then the other thing that we want to talk about is a term that we use a lot is energy efficiency. So if you, I hate when that does that. This is the part I don't like. It's very difficult to get rid of this. There it goes. Energy efficiency rating. Oh, my computer's having a hard time keeping up. Sometimes referred to as EER. And you'll see this rating on air conditioners. And it basically, and sometimes it's referred to as British thermal units or BTUs. It just stands for British thermal unit. But anyways, how do you calculate that? Well, I'm glad you asked. So the energy efficiency rating is equal to the cold reservoir heat divided by time 1 and the work divided by time 2, and I'll define what the time is. So let's define these. QC, this is your heat transfer from the cold environment, lower temperature. T1 is just time. Now this is the wonky part. It has to be in hours. We're so used to doing seconds. W is work. And T2 is time 2, the second time. Also in hours. That's the word hours. And we, unfortunately, we don't have a lot of examples, but like, well, I imagine there's probably, I don't have an example in the book, but there's probably a homework problem. But I think it's probably going to be straightforward. There's a time and then a second time for the work that's being done, and they'll spell it out for you. But that's it. That's the section. You guys have any questions?